And that's a shame. This is not, is it like reversed? Well, you guys can tell it says data 8 anyways. Um, all right. So today talking about updating predictions. Today's lecture is actually pretty much unrelated to any other lecture in this course other than maybe the introduction to probability. So this isn't really like building on the classification and regression stuff. It's actually like completely different, but it's almost like a self-contained lecture. It's really fun. Actually, when I was in grad school, I did pretty much all my research around the stuff that we're going to cover today. So it's pretty fun for me to talk about it. And yeah, that's pretty much it. And then today is actually basically going to be the last lecture that we have kind of new material from the textbook. We will have some kind of like special topics lectures next week that are going to have to do with kind of building on material from the class, and like stuff next week will be on the final exam. But in terms of just like really a bunch of new material that you're going to learn, like today's pretty much the last day. So it's pretty exciting. Um, and so a few announcements. So this week, a lot of things are canceled: office hours, discussion, lab, tutoring sections. There's no more lecture as well this week other than today. So that's pretty much it for this week. We also have no more vitamins. So congratulations to everybody on that. So we're done with vitamins for the semester. Um, we have homework 12 due next Friday, project 3 due next Friday. Again, last project, last homework. So pretty crazy, like almost done with the semester now. Um, and one last thing, which is kind of cool. So course evaluations just went out. So you should be able to fill out evaluations for the entire course. And then we also have a final feedback form. It's at the end of homework 12. You can also just access it from the link here in the slide. So if more than 80% of the class fills this out, everybody gets 2 bonus points on the final. So everybody should do this. So you guys all work together to make sure everybody fills this thing out, both of these. So this is a good incentive for you guys. So it's just like a freebie right there, 2 points for everyone. So yeah, so please do it. Maybe not right now, but at some point today. So yeah, cool. So that's up for announcements. A couple things I wanted to go over. We didn't get to go over this at the end of last lecture. This is just like the last few slides, and when we were talking about classification. So we went through like building our classifier and all that stuff. There's a few things, just caveats I wanted to mention, and these are really important. Like these are like knowing how to do classification is important, and if you're gonna take additional classes in data science or machine learning, you'll learn other ways to classify besides just nearest neighbors. But these things about classification in general are really important. They also apply to regression too, actually, but specifically for classification, very important. So firstly, there's this idea of having diversity in your data. So let's say you're trying to build a classifier that takes in an image. So an image is actually, if you think about it, an image is just a bunch of pixels, and then each pixel has like an RGB value from like 0 to 255. So like red, green, and blue, they all have like 0 to 255. So you can basically represent an image as just like a bunch of numbers. So if you think about it, like images are numerical data. But we had this way to like graphically represent them nicely as like colors. But basically, if you have a classifier that takes in an image and then outputs either dog or wolf, that's like what you're trying to build. And let's say this is what your training data looks like. So you go out, you get a bunch of pictures of dogs and wolves. And so this is kind of the images you have. What might happen is if a lot of your images just look like this, what might happen is if you have a new image that comes in like this on the right, your classifier might mess up and think that it's a wolf. Um, and the reason for this is because the background in your training data, most of the background with the wolves was white and snowy. And then with the dogs, it was like all kinds of like grass and leaves and whatever. So that's going to bias your training data. And so when this kind of situation happens, this is called overfitting. So this means that your machine learning model has overfit to your training data. And the reason for this is basically because your training data wasn't diverse enough. It wasn't representative enough of kind of everything that's out there in the world. So this is just a really important thing to do, whether you're doing classification or regression, but just in general in machine learning, you want to make sure that you have diversity of data. It's just so important. And there's some problems where like there's this like small tail of just like really rare examples that are like really weird and different, but you have to try to get those in your training data as much as possible to make sure that you have like your model is going to perform well everywhere. So that's just like really important. So basically, basic idea there is you want to have a representative sample that's representative of your entire population. And so you want to make sure like both your training set and the test set accurately represent your population. So you want your training set to represent your population because that's what you're using to build the model. So the model is not going to know anything about like weird cases if you don't have them. And then your test set also needs to represent the population, because if it doesn't, then when you finally evaluate your model and say, okay, this is how good I think my model is going to be in the population, that that like evaluation of like how good it is needs to be representative of like how good it's actually going to be in the population. So you don't want to like try to boost your results by like picking a test set that just has like easy examples. Like you want your test set to also be representative of the entire population, so you have an accurate estimate of how accurate your model is. So that's the basic idea there. And then, as I mentioned, overfitting is when you have a classifier, or in general just a machine learning model, that does really well on your training set but can't do as well on the test set. And in general, like can't do as well on the entire population. So this is a very common problem that happens. And typically the solution is like get more data and specifically be smart about it. Like get data that's rare and representative of like things that like edge cases that can happen in the population, basically. So that's just a good thing to keep in mind. The other thing that we didn't get to mention was about standardization. So a lot of people were mentioning this during the lecture last week, like why don't we use standardization? Or like, do we have to do that? So here's a really good example of why you should use standardization in general. So this is that chronic kidney data set that we had. So we had all those different variables from like test results from like maybe like a blood test or something. And so the idea here is that if your attributes on really different numerical scales, the distances can be affected. So a good example of this is, let's look at the second row and the fourth row. So the second row and the fourth row, if you look at glucose, right? If you look at these two individuals, let's say you want to know like how close or how far they are, right? We're going to use that Pythagorean theorem basically to do this. So if you're just looking at glucose, like let's say the only variable you care about glucose, then it looks like they're quite far, because like 157, that's like more than twice as big as 70. So like this seems like this person at 157 is like really far away from glucose. And then now if you look at white blood cell count, right? Here they're at 11,000, this person on the fourth row, and then the second row they're at 12,000. So if you're just looking at white blood cell count, it seems like they're not that far apart. Like 11,000 to 12,000, that's just like about 10% off. You're not that far off. These are pretty close to each other if you think about it. But the idea is if you were making a distance formula using both of these variables, right, then something interesting is going to happen here. Remember, the formula for distance is you take these two variables and subtract them. So you do 157 minus 70, right? And then that's going to give you something that's like around 80-ish or 90-ish. And then if you do 12,000 minus 11,000, that's going to give you something around like 1,000. So it seems like if you're just taking those differences and then like squaring them and then adding them together or whatever, this difference actually seems like it's really large all of a sudden, because you have like this distance, which is like really tiny. This is just like a difference of like 90, but this is a difference of like 1,000. So all of a sudden it seems like if you're looking at the entire distance calculation, the white blood cell count is contributing a lot more to that distance calculation than the glucose is. And so that's kind of like weird. It doesn't really make sense to do that here. And the main issue this is happening is because white blood cell count is just on a completely different scale. The numbers are just a lot larger. So in general, distances are going to be a lot larger. And then glucose is on such a small scale that like distances are going to be like not that big. It doesn't even matter. Even if like glucose was like 0 and this was 157, you might still think that they're close because the white blood cell count is like only different by like 1,000, which is not much relative to all the blood cell counts that we have. So the correct thing to do here would be to standardize each of these columns. So if you can standardize each of these columns, then you'll see that, oh, actually in glucose, I'm like 2 standard deviations above this other guy. But then in white blood cell count, I'm only like 0.1 standard deviation. So like I'm actually not that far. But then you can actually basically have a way to say, how far are you from someone in standard units? And then all of your columns become comparable. And then you can calculate distances like appropriately then. So if you go back to the demo from last lecture, towards the end, there's a couple of examples there. We didn't get to do this in lecture, but you guys can try it out. And it basically does like a before and after comparison of trying to build a classifier if you don't standardize and if you do standardize. And you'll see that if you do standardize, you actually get like better accuracy when you do that. And that's why do you get better accuracy? Because you're just getting more accurate distances. Your computation of like how far things are is just much better. So you can find that like decision boundary better, which means that you can make those predictions better. So that's basically what happens there. So yeah, I mean, in general, like if you know all of your variables are on the same scale, like, or they're all the same units or something for some reason, then sure, I guess you don't have to standardize. But like in general, it's pretty much all the time, they're all going to be on different scales. You're going to have some variables that are like always like just small little percentages, and then some that are like in the thousands. Like it's going to happen. So it's a good practice to just always standardize. Like pretty much always standardizing is like strictly better than not. So you should just always do it anyway. It's just a good idea. Cool. So this is kind of why you might do that. And so that's kind of closes the discussion on um, classification and machine learning in general. So now on to like the bulk of today's lecture, which is updating predictions. So again, this isn't really in the context of like classification or anything. If anything, actually, this is going to go back to the first lecture that we had about probability. So, you know, there's basic things that we talked about probability when we had like 3 cards and like what's the probability of getting a queen and then a king and whatever, and all those different combinations of things. So this is going to be very related to that. And the idea here is that like probabilities of things can change if you have additional information. That's kind of the basic idea here. And so you might want to update your predictions based on just like what information you have. That's the basic idea here. And so the main example we're going to use here is actually, this is a study that happened at Harvard Medical School. So there was like some disease that has a really low prevalence in the population. So what that means is like not that many people have the disease. There's actually like 1 in 1,000 people in the population have the disease. So it's like super rare. And then there's some test that has been created that can determine whether or not you have the disease. And then this test has a false positive rate of 5%. So what that means is like, even if you don't have the disease, there's like a 5% chance you're just going to get a positive result on the test. So like accidentally, you're going to get a positive result sometimes. So that's what that means. So, you know, if you don't have the disease, there's still a 5% chance that like when you take the test, it's going to come out positive. And so the question was basically the reverse. So they kind of flipped that on its head and they said, okay, well now let's look at the other situation. What if we know that your test result is positive? What's the probability that you actually have the disease? So basically asking the opposite question. And all they knew was basically like just these 2 facts, really. Like what's the prevalence of disease? How common is it in the population? And then kind of like, how good is this test when you don't have the disease? Those are the only 2 pieces of information you have. And so they asked this question to a bunch of like Harvard medical students and like attending physicians and like really, really smart people. And then basically what happened was only like 11 out of the 60 people in this like survey got the right answer. So about 18% got the right answer. And almost 50% of the people got the wrong answer. Or well, actually 82% technically got the wrong answer, but 50% answered with the same wrong answer. So the most common wrong answer was that the answer is 95%, because they were thinking, okay, well, if I don't have the disease, the probability of getting a positive is 5%. So then the opposite is probably just 100 minus 5%, but 95%. So that's probably the logic they're using. And this isn't the correct answer. So the goal of today's lecture is going to be to kind of get to that correct answer by the end of the lecture, and in such a way that you guys understand really well how do we actually calculate the right probability, like the answer the right way. So that's going to be kind of the goal of what we're going to be doing today. And so if you are somebody who's like planning to go into medicine, please pay attention. Today's lecture is probably like the most important lecture I would say for you in this entire course. If there's one thing you take away from this class, it should be like what you learned today. So please pay attention if you're going to become a doctor. All right, so in order to answer this question properly, we need to understand conditional probabilities really well. And just like the concept of like, what is a conditional probability? What does it mean? And so to kind of build up the intuition for this, let's start with a simpler example. So let's not talk about diseases right now. We're going to do like a slightly different example. So here's going to be kind of the setup. So there's some class, and it has 60% of the class is second years, and 40% of the class is third years. So there's like only second years and third years in this class. How do we know that? Because these probabilities add up to 100%. So that means there's nothing else in the class. It's just second years and third years. And then we also know that 50% of the second years have declared their major already. And we know that 80% of the third years have declared their major. Okay, so these are some things that we just know about the students. And let's say I pick a student at random from this class. So then the question is, which is more likely? I just pick a student at random from the class. Are they more likely to be a second year or a third year? What do you guys think? Cool. So pretty much everybody's saying second year. And so how do you know that? Well, because 60% of the class is second year, 40% of the class is third year. So there's more second year people than third year people. So that's the correct answer. All right, so now let's try a slightly different scenario. So it's actually gonna be the same exact setup. We have the same class, 60% of the second year, 60% of the class is second years, 40% is third years. And we know that 50% of second years have declared their major. We know that 80% of third years have declared their major. And so then the question is, let's say I pick a student at random and I know that the student has declared a major. So I have some extra information for you this time. So not only have I just picked a random student, I also know that they declared their major. Now, what do you think? What's more likely? Are they a second year or a third year? Yeah, so most people are saying third year. Now, you guys were able to answer that really quickly without even doing any of the math, right? Like you guys didn't literally calculate like what's the probability here, but you knew that intuitively, right? It makes sense. Like, yeah, there are more second years than third years in this class, but like 80% of the third years have declared their major. That's a lot of third years who declared their major, right? If you kind of divide the class into these two buckets, right? Like you have your second year bucket and like your third year's bucket, and the third year's bucket's a little bit smaller, but a lot more of that bucket is declared versus only half of the second year is declared. So it seems intuitively like more of the third years probably are declared. So it means that like if we did see somebody who's declared, like there's probably a higher chance that they're actually going to be third year. We don't know for sure, but it seems like it is. So this is just intuition, but let's actually like verify this in our data. So if we head over to the demo here, we have all these students in a table here. So this table has 100 rows. And so 60 of the rows are going to be second years, 40 are going to be third years, and then 50% of the 60 second years are going to be declared, and then 80% of the 40 third years are going to be declared. So that's kind of already set up here in this table. So I'm just showing the first 3 rows here, but you guys can kind of verify. And so if we wanted to see kind of the breakdown of like how many second years are declared and how many second years are not declared and how many third years are declared and all that. So if I wanted to see all that in a table, what's one way I could do that? So to see like all the combinations of like declared and not declared and like second and third year, like what's one way I could do that? Yeah, so some people said pivot, some people said a group with 2 columns. So you could do both here technically. I personally would prefer pivot just because it's like a little bit easier to visualize. It takes up like less space to visualize everything. So if we do a pivot here, we can do students.pivot, and then we pass in major and year. And so now we can see kind of year here on the left. We have second year and third year, and then on the top we have declared and undeclared. And so let's just kind of go through and verify these numbers really quickly. So we said that 60% of the class is second years, right? So that should mean that everybody in this row should be 60% of the class. So if we sum up these two values, we get 60. So that makes sense. And we can check the same thing for third year. So third year should be 40% of the class. So we can add this up, 32 plus 8 gives us 40. So that looks good there. And then similarly, we said that 50% of the second years are going to be declared. So we have 60 people and then 30 of them are declared amongst the second years if you're just looking at this row. So that seems to check out fine. And then we said 80% of the third years are declared. So if you go to the third years here, looks like 32 out of the 40 are declared. So that also seems to check out just fine. So like those things are looking kind of as expected here. And we can kind of even do the math here too, just to make sure. So, if you want to make sure 60% of the students are second years, you can like do the math here for yourself. So basically take 60, which is the sum of this row, and then divide it by the sum of everything, which is 60 plus 40. So that kind of checks out properly. And then you can also verify kind of 50% in Python as well. So 30 over 60, that verifies that 50% of second years are declared. And then lastly, can do the same thing for third years. So 32 over 48 gives you 0.8. So you can just kind of check these in Python as well. And so now if we want to kind of answer our actual question, which was we picked out someone at random, we know that they're declared, what's more likely, second year or third year? So if you look at this, first of all, let's visually try to look at this, right? So if we know that they're declared, we know that they're going to be in this first column. So if we have a random student that we picked, we know that they're going to be in this first column now. So now if you're looking at just this first column, right away now the answer becomes really clear that third year is going to be just a bit more likely. So there's 32 people who are declared at third year and then 30 people who are declared in second year. So if you're looking at just declared, you're basically just in this column. And so now we know that basically there's more third years that are declared than second years. So that gives you kind of the answer for the actual answer of why it is the case. And so essentially, if you wanted to write this down in terms of like how you'd write down the probability, this is kind of essentially what we're trying to calculate here. So like, what's the probability of third year, of the student being a third year? And this is a kind of like something that this like vertical bar means given. So like probably being third year given that we know that they've declared their major already. That's essentially what we're trying to calculate here. And so if we just look at this column, we can calculate this by just taking 32 and dividing by everything in that column, which is going to be 32 plus 30. So that's just going to be 62. So basically 32 divided by 62, that gives us probability of being a third year, given that you declare. So this is going to be 52% roughly, which is slightly more than 50%. So it seems like third year is more likely than second year. So now you have kind of like the actual example there. And then if you wanted to know the probability of second year given declared, just kind of do the opposite thing. So go up to the table. We have 30 people here. So it's just going to be 30 divided by 62. And so that probability is 48%. So that just kind of verifies that as well. So any questions about this and how we did that? Okay, cool. So it seems pretty clear. Yeah, can I review that again? Yeah, so if I go back again to this part here, the idea was we kind of broke down all of our students based using the pivot table. So the pivot table just kind of put the students into the actual categories that they're in. And again, how is this determined? Well, firstly, 60% of the students are second year. So that's why we have 60 people on this first row. And then 40% are third year. That's why we have 40 people on the second row. And then within that, we also know that half of this second year students are declared. So that's why it's like 30-30 split. And then 80% of third years are declared. So that's why you have 32 and 8 as your split for third years. So now that we have all the information, we can basically use that information to like fill out this table now. And then the next thing we want to do is now that we fill out this table, we want to calculate what's the probability of someone being like a third year given that they're declared. Well, if you're trying to calculate the probability, all you have to do is just look at the column that's talking about what you want. So if you're saying given that they're declared, that means that you can ignore the other column. You should be only looking at the declared column. And then now that you know it's given declared, then you just need to figure out, okay, given that we know we're in this column, what's the probability of each of these things? Well, the probability of each of these things is just going to be whatever the number is for that row divided by the total count. So that's kind of what we're doing there. So 30 second years divided by 62 gives you declared, or probability of second given declared, and so on. So this is how you could do it kind of with a pivot table, which is great. But in practice, you might have like more complicated scenarios. It might be kind of difficult to do it like in a pivot table. You don't always have to like draw a pivot table and write everything out every time. So the idea is, can you answer this question like a little bit more easily without having to look at a pivot table? And so the answer is yes, we can do that. And so that's what we'll go over next. So if you wanted to actually answer that question, the exact same question, but using slightly different method, which doesn't require even Python necessarily, and we just maybe want to do it by hand really easily, we can do this using Bayes' rule. And so Bayes' rule kind of helps you calculate conditional probabilities when you know kind of almost like the opposite scenario. Like we're trying to calculate probability of declared, or sorry, we're trying to calculate probability of being a third year given that they're declared. And one thing that's interesting is we know the opposite probability almost. We kind of know the probability, I shouldn't say opposite, but like we know kind of the probability when you switch those things. So we know the probability of being declared if you're a third year. We know that from the beginning, that's 80%. So it's kind of interesting, like you know kind of like the other probability when you switch them. And so that's kind of what Bayes' rule helps you do, is if you do know like kind of, if you can switch them and you know that probability, you can actually try to use that to calculate what you're trying to get to. And that's the basic idea. And the idea is you also want to kind of like update your prediction based on new information. So what this means in the context of what we just talked about is like, we knew beforehand that 40% of the class is third year, but now we have new information. We've taken a random student, but there's some additional information now. We know that they're declared. So now the prediction for what's the probability of them being a third year has changed. So the idea is like we're updating what we think based on new information that we have about the student. And so Bayes' rule kind of helps you answer questions in those type of situations. And this second bullet point might be a little bit confusing, but basically what it's saying is like, if you have like multiple stages of like information that you're getting, then the chance of an event at an earlier stage, you're trying to find the chance of an event at kind of the earlier stage given the result at a later stage. So we'll go over like what that actually means here in terms of like an actual example. So what we're going to do basically is we're going to draw out all of the different ways that things can happen, like different combinations of students basically using a tree diagram. So this is going to be kind of the way that we represent the world probabilistically. And it's going to help us answer this question like a little bit more easily. So there's almost kind of like two steps when you're picking a student from the class. You can think of it like that. So firstly, you have, when you first pick them up, you have this, they can either be a second year or a third year. And so we know the probability of being a second year is 0.6, 60%. You know, the probability of being a third year is 0.4. So we're just gonna write the probability of kind of like each event on like each of these branches of the tree. And then once we go into second year or third year, then there's like additional branches as well for each one. So we'll kind of write those out. And so this initial branch that you have, we're going to call this the prior probability. So this is just terminology that you use when you're talking about Bayes' rule. And the reason we call it prior is because this is what we think the probability of a student being second or third year is if you don't have any other information about them. So if all we know is that like there's a student in this class, this is what we believe like beforehand. That's what's called prior. And then once you have that, you can split out what the different possibilities are if they're a second year or if they're a third year. So if they're a second year, there's a 50% chance they're declared, and there's a 50% chance they're undeclared. So this branch is just going to be 1 minus the top branch. And that's going to be true in general. Whenever you have like a branching in the like probability tree diagram like this, the branches have to like sum up to 1, because that's like all the different possible things that could happen at that like, fork. And then if you go to third year, then in this case, we have an 80% chance of the declared. So we knew that up front as well. We were kind of given that in the slide. And that means that there's a 20% chance of the undeclared. So essentially what we've done here with this tree diagram is we've written out everything that we knew beforehand. So before we like did anything like draw a student or anything like that, this is just writing out all the information we had in that slide. So the slide told us 60% of the students are second year, 40% are third year. Once you know that they're second year, 50% declared. Once you know they're third year, 80% declared. So we're just kind of writing all that out here in a tree diagram. And so this is just kind of like the given information basically. And so the prior probability is essentially saying like, this is the probability that we think a student has of being a second year or a third year if we don't have any other information about them. So it's like prior to getting that additional information. Now, once we get additional information that like, oh, they're actually declared, so we have some additional information about them, then you're going to update your probability, and then you're going to come to a posterior probability. So that's the main difference here. So you have kind of, this is what we think beforehand if we don't know anything about the student. These are the kind of the two possibilities of the world. But once we know additional information that they're declared, and we're trying to get back to like, okay, what's the probability of these two things? That probability gets updated. So then it becomes a posterior probability once we have that information going. So that's just kind of the terminology for how you're thinking about like updating probabilities basically. And so in the context of like Bayes' rule, these probabilities here, these are called likelihoods. So these are kind of like just likelihood of like the actual event that you end up seeing, because you end up getting additional information. So likelihood, think of that as like, that's like the additional information that you end up seeing. Whereas prior probability is just like what you expect for the probability you care about beforehand. So remember in the demo here, we wrote something like this. So we said probability of third year given declared. That's how we wrote this. So just probability of third year on its own, that would be the prior probability. So that's like the probability without any information. And once you're given information like that the student is declared, then this would be considered a posterior probability. So you've like added information, your probability is going to change a little bit now. That's the basic idea here. Yeah, so this is kind of the tree diagram for the setup that we had. And so the idea is if we wanted to actually calculate kind of the probability of them being, let's say like a second year, given that they're declared, right? Then we need to kind of do something a little bit different here. And so one thing we can do is we can basically say, okay, pick a student at random, and we know that they're declared. So if we know that they're declared, we can actually take out this undecided branch. So just take out both of the undecided branches because we know that they're declared. So we know that the kind of universe we're in now for the student is going to have to be along one of these two branches. So we know that now. And so that's one first step that we can do. And then if we want to actually calculate the probability, what we can do is we can say, well, let's calculate the probability of going along this branch. and the probability of going along this branch. And then we can figure out like kind of the total probability of this happening. And then all we need to do is the probability of the branch that we care about, just divide that by the probability of both branches. So for example, if you wanted to know the probability of, like, let's say someone being a second year, given that we know that their major is declared, how could we calculate that? What we could do is calculate the probability of this top branch and just divide it by the probability of both branches. Because technically the probability of both branches is going to give us what's the probability of them being declared. And so that's how we can do that. And then how do we actually calculate the probability of a branch? You can just multiply the probabilities through the branches. So the probability of being like second year and declared, that's just 0.6 times 0.5. And the probability of being third year and declared, that's 0.4 times 0.8. And so once you have like those individual probabilities, then it becomes a little bit simpler to calculate the probability that you actually want to calculate. So to calculate the posterior probability, just to kind of show you a concrete example of how you would do this. So if I wanted to know the probability, let's say, of being a third year, given that they're declared, I calculate the probability of this branch, and I put that on top here. So that's 0.4 times 0.8. And then I divide by the probability of both branches. So I just add each of the branches individually up. So I have 0.6 times 0.5, that's what goes over here. And then I have 0.4 times 0.8, that's what goes over here on the bottom right. So that's essentially how we can do it. And then we get to the same answer that we had in the notebook, which is about 0.52. So again, just to recap that here, the probability of, third year, so probability of something in this like earlier phase, given that we know something in the later phase, how do we do that? Well, first, cut out the branches that have nothing to do with this later phase. So we know the later phase is declared. So let's just take out everything, all the branches that have nothing to do with undeclared. Once you take out those branches, then it's just a matter of, okay, now let's just figure out what are the paths that I care about and what are the paths that I don't care about. So the path that I specifically care about for this problem is third year declared. So that's the path that goes on top. And then what goes on the bottom, it's just all the paths summed up together, all the paths that are kind of like left now. So that's kind of how we would do it. So any questions about that process? Okay, cool. And so, let's say, for example, you're trying to do something different. Like you wanted to know the probability of third year given that they're undeclared, right? Like how would you do that one? So that one you would do you'd kind of follow the same process, but you'd cut out the branches that have to do with declared and just look at the undeclared branches. But then the math would be kind of done in a similar way. So like take the path that you want and then divide it by probability of like both paths. So that's basically it. So one question is 0.6 times 0.5. That is this itself is actually a probability too. So 0.6 times 0.5, that's actually the probability of getting a student who is second year and declared. So given you don't know anything about them, they're probably getting second year and declared. That's actually what that probability is. And then the probability on this one here is the probability of getting third year and declared. So there's actually, those are probabilities themselves too. But this is just how we kind of calculate this entire conditional probability. Typically conditional probabilities involve kind of like a ratio of two different kinds of probabilities. Cool. So now let's go back to the clinical trial case that we had with the Harvard study. So let's try to answer that question now. So we were given a few pieces of information there. So firstly, we were given that the disease has a prevalence of 1 in 1,000, meaning that it's pretty rare to get the disease. So what that essentially means is that's our prior probability. So if I have a patient come in, I don't know anything about them, they haven't taken any test, their probability of having the disease should be 1 in 1,000. So that's going to be kind of the prior probability. So we're just writing down that given information here. And then we were also told that it had a false positive rate of 5%. So we said false positive happens when you don't have the disease, but you test positive. So that's what you're writing here. If I don't have the disease, the probability of testing positive, that's 5%. So I can fill out that part of the tree now too. And then we can fill out the bottom branch as well, because that's just gonna be 1 minus this thing. So this one we know has to be 95%. So if you don't have disease, there should be a 95% chance of testing negative. So that seems about right. And then now to fill the branches on top. So that's information actually that we weren't given. So if you go back to that slide, we actually didn't give this information here in terms of like what's the probability of testing positive if you do have disease. But what we can do is we can just kind of assume that that probability is going to be 100%. So yeah, so this is basically just saying the problem didn't actually give the true positive rate. That's what this branch here is, the true positive rate. So if you have the disease, what's the probability you actually test positive? But we can just assume this to be 100%. So let's assume that it's 100%. So like if you do have the disease, like the test doesn't fail. It's gonna like for sure pick you up and say you have the disease. So if we do know that, let's just update the graph now to say that this is 1, and then this one is 0. All right. And so now we have the entire graph, the entire tree diagram filled out. And so now the question number was asking if you've tested positive, given that you've tested positive, what's the probability you actually have the disease, right? So the first step for this tree diagram, if we're trying to figure that out, and we're just talking about like something given that tested positive, what's the first thing that we would do here? The first thing we would do is cut out all the branches where you're testing negative, because we know that's not in consideration anymore. We know that the person is tested positive. So let's take out those 2 branches. So now we just have these 2 branches left over that we care about. And then the question was asking, what's the probability of disease given that you've tested positive? So that means that this branch is the one that's going to go on top in our calculation. And then in our like denominator on the bottom, we're going to have just the probability of like both branches together. So if you can just write this out, we're trying to calculate probability of disease given that we tested positive. So we remove the negative branches. And then we said, okay, well, on top, we're going to have the first branch that we care about, which is disease times being positive. So that's 1 in 1,000 times 1, and then divided by kind of both of the branches, rather. So you have probably this entire branch over here, and then probably this entire branch over here as well. And so now we can actually calculate the probability. And so if you do the math for this, you get like 0.019, which means like 2%. So that means that if you actually test positive on this disease, on this test, you only have a 2% chance of actually having disease, which is kind of crazy because it seems like the test is not that useful. There's like basically a 98% chance that you don't even have the disease, even if you test positive on it. So it seems like the test is just kind of like useless. So it's like kind of weird, but that's actually the answer. And we'll go over like why it's not actually useless. But first of all, this is kind of, this is just the actual value that you get. So I'm getting a few questions like, why did we assume 100%? Just because I said so. So that's just something that I'm giving you. I'm giving you that you can safely assume that if you have the disease, you're going to get positive. So that's going to be given to you always. If we ask you this like in an exam or like something like that, you'll have this value on top. So you don't have to worry about that. I just basically gave you that this time. Cool. So now let's check out why is it 2%? Like that's so weird. It seems like this test is like kind of useless. So let's actually like take a look at what's going on here. So there's this function that we've created up at the top called create population, which allows us to just create a population according to like how prevalent a disease can be. And it already has like the positive rate and all that stuff like built into the function. But basically we're gonna make that population here, and we're gonna make a population of, let's say, like 10,000 people, and then the prevalence of disease is 1 in 1,000. So I'll explain why we have this as an actual like input into the function. We're actually going to change this later on in the lecture. But this is how we're going to make it. So if we make our population using these parameters, we basically now can see our data in terms of disease and no disease. And so we can see that we have 10 people who have the disease, which makes sense because the prevalence is 1 in 1,000, and you have 10,000 people in the population. So 10,000 times 1 in 1,000, like divided by 1,000, is just 10. So this seems correct here. So we have 10,000 people who have the disease, and then how many people don't have the disease? Well, that's going to be 9,990. So that's correct here. So that looks good. And then we also said that we knew that if you have the disease, it's a 100% chance the test is going to come out positive. So if we look at the top here, if you have the disease, 100% chance of being positive. Yep, that seems correct here. So all the diseased people are in the positive side. Nobody who has disease is going to test negative. It's just not possible. All right, so that looks good there. And then finally, we said that the false positive rate is 5%. So the 9,990, 5% of that should be in the positive section. I think this number might be like a little bit off actually, but it's like roughly correct. And so that's kind of the basic idea here is we can see that roughly 5% of the people who don't have the disease are going to be testing positive here. And so if you wanted to see what's the probability of having a disease, given that you tested positive, well, we can calculate that again using the same thing that we did last time. So if we know you tested positive, that's just going to be this column here. So we can ignore the other column. It's kind of like ignoring the other branches. So if we know that you tested positive, you're going to be in this column. And so at that point, if we want to know what's the probability of having disease, well, we can simply just take 10 and divide that by everything in this column here. And so this is analogous to what you're doing with the branches. You're taking just the branch that you care about and dividing it by the sum of both branches. So that's what essentially we're going to do here. We're going to take 10 and divide it by 510. So take 10 divided by 510, and we get 0.0196. So it's, again, we get that like 2% value there. And then if you wanted to calculate this using the, oh, this is kind of weird. Yeah, I don't know why this is getting such a weird different number here. Oh, this is the prior probably is 1/10. Oh, sorry. That's like a little bit ahead of what I wanted to get to. Yeah, so that's kind of what we could say here. Is this is the probability is 2%. Now, this seems like this test is useless because like if you test positive, there's only 2% chance of actually getting, actually having a disease. And so in practice, what would happen is this, again, this is like if any random person in the population took the test, right? In practice, what would happen is not any random person would take the test. Like you typically would only take the test like if you have symptoms, like you actually came in to see the doctor for something, right? And so in that case, your chance of having a disease beforehand is actually already like higher than normal. It's not just like taking a random person in the population and testing them. So there's something else that usually comes into this, some other information that typically like goes into this before you even like take the test. And so one way to think of that is basically what you're saying is that my prior probability for you having a disease is actually already higher, because if you're trying to go in and take this test, like before I even get the results back, the fact that you want to take this test means that you already think you have it, or maybe the doctor already thinks you have it. And so that probability beforehand is already like kind of high to begin with. And so that's kind of how we can try to model that as well in terms of thinking about, okay, we actually think your prior probability beforehand is like a little bit higher than normal. And so if you wanted to actually model that, we can do that using subjective probabilities. So subjective probabilities kind of exist already in the world today. Basic idea behind them is that you already use this today kind of when you're like evaluating decisions in your life, like whether you want to do something, like if you're super risk taking or not, or whatever, like you might want to do certain things that are like kind of risky or whatever, you're probably already evaluating probabilities in your mind. And like everybody has different subjective probabilities about things. So you kind of already have this, but you don't really think of these as like numbers in your head, like, oh, the probability of this is 90%, so I'm going to do it, or whatever it is. But it is in general like something that you do and think about. And so the idea is, there's two ways to think about the probability of something happening. So one is kind of the frequency with which it would occur if you did it like many, many times, right? So you think about like a coin flip, right? What does it mean to have a probability of 0.5? Well, one way to interpret that is like, well, if I just flip this coin like many, many times, roughly 50% of the time, it's going to come up as heads. And so like that's how you could define the probability. But they can also be like a subjective belief that it will occur or that it has occurred. And so that can be useful in like some other context. So for example, if I go to the doctor's office today and I'm feeling kind of sick, I might have a subjective probability of like how sick I am. Like maybe it's like a 30% chance I think that I have something, I have some disease. And so that's a subjective probability. So that's not a frequency probability where like in my mind, I like simulated myself like a million times and then like determined that like, oh, 30% of the time I actually ended up having a disease. Like that's not what I did there. So that's the basic idea, is that you can have like two different ways to think about probabilities in general. And so why would you use subjective priors? So one way you might want to use this is if you're trying to quantify a belief that you have and it's like relevant to a decision that you're trying to make. You might also use this if like the subject of your prediction wasn't randomly chosen from the population. So again, thinking about the case I just mentioned where like, let's say you come into the doctor's office like feeling sick, right? You weren't randomly chosen from the population. You came in feeling sick. So that's a good situation where we might want to use a subjective like probability or subjective prior. We don't want to just use like the frequentist prior, which is saying that like 1 in 1,000 people have the disease. The fact that you came in for some reason. So we think that your probability of having disease before we even take the test might be a little bit higher. And so that's where like a subjective prior subjective probability would be useful. So let's actually see this in practice. So let's say that like you come into the doctor's office and you have some symptoms or something like that. And so in that case, the doctor now thinks that your probability of having disease is actually higher. Their prior is a little bit different now. So their prior probability is actually now 0.1. So you can actually model that as well in this kind of a tree diagram. So the idea is you can have the exact same tree diagram, but now instead of having 1 in 1,000 here, we're going to make this 0.1. And so why would you do this? Again, the reason it might be valuable to do this is because you want to have that answer to be to have like some more meaning to it, right? When you say like, what's the probability of having disease given that you tested positive, that probability should mean something more. Like it should be stronger, it should be higher for somebody who came in with symptoms, right? Versus somebody who like just was chosen at random in the population. So that's the basic idea here. That's why we would do this. So let's assume the doctor assigns like a prior probability of 0.1. Like doctor thinks like beforehand, okay, look, based on your symptoms, I think now, I actually think there's a 10% chance of you having this disease. It's not just 1 in 1,000 because 1 in 1,000 would just be like someone at random in the population. So they can assign kind of a probability here, and then we can basically go through this exercise of like going through the diagram and then figuring out like what that probability would be. And so if we wanted to calculate the probability, if the prior probability is 0.1, we can do that using the same math. So let's say here, probability of disease given that they tested positive, if the prior probability is 1/10. So if the prior probability is 1/10, we can use that same formula, but here we're going to pass in 0.1. And so we'll have 0.1 times 1. That's going to be kind of the probability of, that's going to be kind of calculating this entire branch. And then remember we divide that by the probability of both branches. The top branch is going to be 0.1 times 1. The bottom branch is going to be 0.9 times 0.05. So if we do that now, basically the only thing we've changed is kind of this number went from like 1 in 1,000 to 0.1. And then this number went from like 0.999 down to 0.9. And so with just that little change, now the probability of you having disease, given that you tested positive, is like 69%. So now all of a sudden it's like gone up pretty drastically. And so it's pretty cool to see how the probability now changes quite a bit if you have that additional information. And so if you want to see like why this is the case, we can generate a population here using this function again, create population. And instead of 1 in 1,000, we can pass in 1 out of 10. And so now we get a slightly different breakdown. So if you think beforehand that there's a 1 in a 10 chance of this person having disease because like they're presenting with symptoms or something like that, then this table starts to look a little bit different. So now you have 1,000 people in the top row instead of just 10 people. But again, the breakdown is still the same. You still have 100% of the disease people test positive. You still have that 5% of the no disease people test positive. But now all of a sudden, if you look at this column here, there's way more people with disease than without. And so again, why is that? Because your prior probability has affected the outcome there. And so that's kind of how you could do that. And then let's say like, in addition to you presenting with symptoms, like, I don't know, you've like looked it up on like WebMD and you've gone down a rabbit hole and now you like really, really think you have disease. So now your prior probability is like half, like 0.5, like 50%. So now your prior probability is even higher. So if we do that, we can do the math there again. We can replace this 0.1 with 0.5 here, and then we can replace this 0.9 with 0.5 over here. And so now if you do the math, you get an answer of 95%. So if your prior is like really, really high, then it probably would be even higher. So in actual, and that's kind of like a fun example, but in an actual case, a doctor maybe could do this. Let's say like you came in with symptoms and you're also like immunocompromised. Like we know that you have really low immunity. So there's like, the doctor has even more reason to believe that you might have the disease beforehand. And so that's a case where like the prior might be even higher. And so you can just see here how like the prior affects the results as well. But basically the idea is this gives you a way to incorporate that kind of like subjective belief that you might have into how you might make decisions, how you might interpret the result of something, how you might calculate the probability of something. So that's kind of the basic idea here. So I think we will stop the lecture there, but I'll stay on if there's any questions.